I want to start today with a bit of a puzzle I found while going through the notes for Unit 9. It's about boiling points.
Okay.
Usually in chemistry and physics also, for that matter, we follow a simple rule. No. Heavier things are harder to boil. You increase the mass, the boiling point goes up.
That is the general rule, yes.
Right.
More mass usually means more energy is needed to turn a liquid into a gas.
Right. So I was looking at the data for methylamines. You have a methylamine, dimethylamine, and then trimethylamine.
Yes.
Logic says that trimethylamine, which is the heaviest of the three, should have the highest boiling point, but actually the data says the opposite.
I think I know where you're going with this.
Methylamine boils at around -6 degrees Celsius, but trimethylamine, the heavyweight, boils at just 3 degrees. Why does adding mass actually lower the boiling point here? It feels wrong.
It is a very counterintuitive result, isn't it?
Mm.
And the answer to your puzzle is the core concept of today's deep dive.
Which is classification.
Exactly.
Oh.
It's not about how heavy the molecule is, it's about how it connects with its neighbors.
So that brings us to our focus. We are doing a deep dive into Unit 9 amines, and specifically how we classify them. Now, usually classification feels like the easy part of the chapter, just memorizing labels. Is it really that critical?
Oh, it is actually the most critical part of this entire unit.
Yeah.
See, in your Class 12 syllabus, classification is not just about labels.
Okay.
It is the secret code that predicts everything else.
Mm-hmm.
It tells you how basic it is, whether it will dissolve in water, and yes, it explains that boiling point mystery you just mentioned.
So if you get the classification wrong...
You will predict the wrong chemical reactions later. Guaranteed.
So it's the foundation. Okay, let's strip this down to zero level then.
Mm-hmm.
When we look at an amine structure on an exam paper, what is the one fundamental rule for classifying it?
At the simplest level, we are just counting. That's it. We focus entirely on the nitrogen atom. It is the star player.
Okay, just the nitrogen.
We just count how many carbon-containing groups, alkyl or aryl groups, are directly attached to that nitrogen.
Directly attached. So we're ignoring the rest of the molecule for a moment and just looking at what is touching the nitrogen.
Precisely. If there is one carbon group attached, it is a primary amine, or 1 degree. If there are 2 carbon groups, it is secondary, 2 degree.
And 3 groups would be tertiary, 3 degree.
Perfect. 1, 2, 3.
That seems quite straightforward. But I know students get tripped up here. Where's the trap?
The trap comes from carrying over old habits from the alcohols chapter.
Oh, right. With alcohols, you look at the carbon chain.
Exactly. With alcohols, you check the carbon that the OH group is attached to, and you count its neighbors.
You see how crowded that carbon is.
Yes. But for amines, that is the wrong approach. We do not care about the carbon chain's complexity. You could have a huge, long carbon chain, but if it is only touching the nitrogen at one single point,
It is still a primary amine.
it is still primary. That is a key distinction. For alcohols, look at the carbon. For amines, you must look strictly at the nitrogen.
Don't get distracted by the tail, look at the head.
A very good way to put it.
I want to try and visualize this because 1, 2, 3 still feels a bit abstract on paper. How should we picture these structures in 3D?
Okay, let's do a small visualization exercise, if you can. Just close your eyes. Imagine the nitrogen atom is a central hub, a small sphere.
Okay, I have the hub.
It has 3 potential connection points, like docking stations. And hovering just above it, there is a lone pair of electrons, like a permanent little antenna.
Hub, 3 docks, 1 antenna. Got it.
Now, let's build a primary amine. 1 docking station connects to a carbon group. The other 2...
They must be holding on to hydrogens.
Correct. 1 anchor, 2 hydrogens. Now, let's swap to a secondary amine. What changes?
Okay, so 2 docking stations now connect to carbon groups. That leaves only 1 spot left for a hydrogen.
Perfect. And for tertiary?
All 3 docking stations are taken by carbon groups. There are no hydrogens left on the nitrogen at all.
And that is the part that dictates all the behavior. It is not just about counting carbons. It's about counting how many hydrogens are left.
So that's the what's really happening moment.
Yes. The classification 1 degree, 2 degree, 3 degree is basically a countdown of available hydrogen atoms on the nitrogen. Primary has 2 NH bonds, secondary has 1, tertiary has 0.
And why does that hydrogen count matter so much?
Because those NH bonds are the molecule's handles. They allow the amine to do hydrogen bonding, to stick to water or to stick to each other.
So primary amines have 2 handles. Tertiary amines have no handles.
No handles at all.
Okay, so if I'm writing the definition in an exam, I need to be very precise. What's the anchor definition that I should write?
You should write this. Amines are classified as primary, RNH, secondary, ardent, or tertiary based on the number of alkyl or aryl groups bonded to nitrogen.
That's short and effective. Based on the number of groups bonded to nitrogen.
Correct. And always keep that mental image of the handles in your mind. It really helps with the analogies.
Speaking of analogies, I've heard you use the stool analogy. How does that work here?
Yes. So think of the amine classification like the legs of a stool. A primary amine is like a one-legged stool. It has one big carbon leg.
And a one-legged stool is very unstable, no. You would need to hold on to something.
Exactly. In the molecular world, that holding on is hydrogen bonding. The primary amine uses its two hydrogen hands to grab its neighbors for stability. It's needy.
Okay, so primary is wobbly and reaches out. What about secondary?
A secondary amine is a two-legged stool. A bit more stable, but it still needs one hand to hold on. But a tertiary amine, that is a three-legged stool.
Perfectly stable on its own.
It is self-sufficient. It doesn't need to reach out to its neighbors.
Because it doesn't have any hydrogen hands to reach out with.
Right. And structurally, it doesn't feel the need to. This self-sufficiency is why it behaves so differently.
I actually have a different way I think about it. More of a social analogy. Let's say nitrogen is a parent and the carbons are children.
Okay, I'm listening.
A primary amine is a parent with an only child, just one carbon.
Right.
So the parent has plenty of time and energy to interact with friends, the water molecules.
That works, yes.
A secondary amine has two kids, getting busier. But a tertiary amine, that parent has three children, three carbon groups. They are completely swamped. They have no time to hang out with friends anymore.
That is actually chemically very accurate because of hydrophobicity. Carbon groups are hydrophobic. They dislike water.
Right.
As you add more carbon family members, the nitrogen gets surrounded by these hydrophobic groups. It literally loses its ability to interact with the water friends.
So the tertiary nitrogen is socially isolated by its own family.
In a way, yes. And this is not just theory. Without this classification system, we could not explain real chemical reactions. For example, later in Unit 9, you will study diazonium salts.
That's a huge topic for conversions, isn't it?
Massive. And here's the thing. The reaction only works for primary aromatic amines. If you try to make a diazonium salt with a tertiary amine, the reaction fails completely.
So the classification is like a sorting hat that tells you which chemical path you're allowed to take.
That is a very good way to put it.
Let's solidify this with a mental movie before we get to more applications. You mentioned the pyramid shape earlier.
Yes. Let's direct the scene. Picture 3 nitrogen atoms, each one sitting at the center of a small pyramid.
Okay. Scene 1. Primary amine.
Look at the base of the pyramid. You will see one large dark sphere. That's the carbon. And next to it, 2 small bright white spheres, the hydrogens.
1 dark carbon, 2 white hydrogens.
Scene 2. Secondary amine. The base changes. Now you have 2 large dark spheres crowding in. There is only room left for 1 small white sphere.
The white spheres are being pushed out.
Exactly. Scene 3. Tertiary amine. The base is now full of dark spheres, 3 of them. There are 0 white spheres left.
And the top of the pyramid.
The top, the apex, is constant. That glowing red or orange cloud, the lone pair antenna, is always there, always watching. It's the base that has become crowded and dark.
You know, that visual, it actually solves the puzzle we started with, the boiling point one.
It does. Let's go back to methylamine versus trimethylamine. Methylamine is scene 1. It has those 2 white spheres, the hydrogens.
The handles, as we said.
Correct. We call it hydrogen bonding. Those white spheres act like Velcro. One molecule sticks to the next. To boil methylamine, you have to rip all that Velcro apart. That takes energy.
But trimethylamine is scene 3.
It's scene 3. 3 dark carbon spheres. No white spheres, no Velcro.
So even though it is heavier, the molecules aren't really sticking to each other?
Exactly. They're just bumping into each other and can easily float away. They only have weak van der Waals forces, not strong hydrogen bonds. So, despite having more mass, the lack of stickiness means it boils at a much lower temperature.
That completely flips the logic. It is not mass equals boiling point. It is stickiness equals boiling point.
Precisely.
Does this lack of stickiness in tertiary amines have any practical use? Or is it just a lab curiosity?
Oh, it is very useful. Take water treatment. Engineers use special materials called anion exchange resins to filter pollutants out of water.
Okay.
And these resins are often built using tertiary amines.
Why tertiary? I would have thought you would want something that is friendly to water.
Actually, you want the opposite. Remember your family analogy. Tertiary amines are hydrophobic. They don't interact much with water.
Right. They're the busy parents who have no time for friends.
And in a water filter, you want the resin to grab the pollutant, the anion using that lone pair antenna. You don't want the resin getting distracted by sticking to all the water molecules passing by.
Ah, I see. By using tertiary amines, the resin ignores the water and focuses only on its job, catching pollutants.
That is smart, no. Use the antisocial nature of the molecule to keep it focused.
It is. But I have a counter question. We said the lone pair is always there, and the carbon groups push electrons towards the nitrogen, the inductive effect.
Correct.
So, if tertiary amines have three groups pushing electrons, shouldn't they have the strongest lone pair? Shouldn't they be the most reactive nucleophiles?
On paper, you are absolutely right. They have the highest electron density.
Hmm.
But in reality, especially in a solution, primary and secondary amines often react faster.
That doesn't make sense. If tertiary has the most electron power, why does it lose the race?
One key phrase, steric hindrance.
Steric hindrance.
Imagine you are trying to shake someone's hand. Your hand is the lone pair. Now imagine you're wearing three giant, puffy winter coats.
I wouldn't be able to move my arms properly.
Exactly. Those winter coats are the three bulky carbon groups. Even though your hand, the lone pair, is ready to react, the sheer bulk of the groups physically blocks anything from getting close enough.
So the primary amine, with its tiny hydrogen atoms, can just zip in easily.
Yes, it is much less hindered. So while tertiary has more power, it has less access. It's like trying to get through a narrow door carrying three big suitcases.
That is a crucial concept. So steric hindrance is the key word there for exams.
Always remember it when you were dealing with tertiary amines.
Okay, we've covered a lot. I want to do a quick clarity check for our listeners. What are the gold standard lines to write in the exam for full marks?
Okay, get ready. Note these down. Number 1, primary amines have one alkyl group and two NH bonds. This is important because it explains their ability to form strong hydrogen bonds.
Got it. Number 2.
Secondary amines have two alkyl groups and one NH bond. This means they can still hydrogen bond, but less effectively than primary.
Okay, and the third one?
Tertiary amines have three alkyl groups and NO-NH bonds. And a warning here, do not write that they have no lone pair. They do have a lone pair, they just lack the hydrogen for bonding.
That is a common mistake. Okay, what about basicity in water?
Yes, very important. In aqueous solution, primary and secondary amines are often stronger bases than tertiary amines. This is because of solvation effects. Water stabilizes the ions better when hydrogens are present.
And finally, that reaction rule.
Only primary aromatic amines undergo diazotization. If you try it with secondary or tertiary, you will not get a stable diazonium salt.
This is a favorite trick question.
Only primary aromatic. Perfect. Let's just wrap this up with a quick recap for revision.
Let's do it.
The core idea.
Classification is just counting the carbon groups directly on the nitrogen. 1, 2, or 3.
The mental picture. The 1, 2, 3 rule. Remember the number of white hydrogen spheres decreasing as the number of dark carbon spheres increases.
And the key takeaway.
Behavior is all about the handles, the NH bonds. Primary amines stick together because of hydrogen bonding. Tertiary amines stand alone.
Perfect. It really feels like once you know if an amine is a 1, 2, or a 3, you can predict exactly how it will behave.
That is the best way to approach it. Master this classification and you unlock the rest of Unit 9.
Well, that is all for our deep dive into the classification of amines. Next time you see a nitrogen atom in a diagram, count those carbons and check for those little white hydrogen spheres.
And remember, watch out for those winter coats. Steric hindrance is always lurking.
Thanks for listening. Keep learning, stay curious, and we will catch you in the next deep dive.
Goodbye, everyone.